That's hybrid. So if this is too much for you guys, if you feel like you're too clustered together, you guys can go to the other room and just hook up to the Zoom, okay? Does anyone wanna look up the Zoom? Or do you guys just wanna stay in person? Up to you, it's okay. But you have to speak up, because it's getting hot. And it's getting hot.
Oh, look, it's
Another room or you're gonna look to I really genuinely do apologize for this. It shouldn't be like this. It should be like for you right now. So we're just gonna try to make the best of it and then we're gonna. What did you do? But before you. I haven't called the app. The mic. So I think that's the front. I never used it on that. Do you have it?
Yeah, I know. I didn't finish it, so we got a record. Yeah. Like, I don't know when to find out. And then I just think it is.
Environment for the hydrants is the same, so they are.
They do it thing, like they're like.
So it goes split down the middle.
Yeah.
Oh, yeah.
No, I don't actually. They were giving.
Actually, yeah.
About 80. So, not even close, 50. Close to 50%, not even 20. Okay, that's fine. Okay, so either way, we already did the three of here. Do you guys want me to go over them again? Yes, okay. Okay, let's go through them again. So, okay, again, we're just counting the number of signals now. As we talked before, number of signals is just the number of unique environments, okay? It's just unique environments. Now, before you even look at the environments, you have to see if there's any symmetry in the molecule. Why is symmetry important? Why is it so relevant? What does it matter? Exactly, they're gonna reflect each other. So whenever you have any planes of symmetry, that means that you're only gonna look at one of those planes to find the number of signals that you have. That's why in this case, we were tracing a line down the middle. We're just gonna look at the left side in this case. It doesn't matter if you wanna look at the left or the right side. They're the same exact thing. Now, again, unique environments. We have a methyl group, a carbon that has 3 hydrogens. That's the only one that has that characteristic. It's the only one that has 3 hydrogens, so unique environment. Now, in here, we don't have anything because remember, that double bond, it's fulfilling the octet, so we can't add anything else in there. Now, the little baby hydrogen that's right in the middle, again, unique environment. Now, we were talking about these guys and distereotopic. Really quickly, what was distereotopic? What does it mean?
On the same side.
Same side, cis and trans, yes. So distereotopic, it sounds like distereomers, which hopefully you remember from chapter 5 back in Org 1. If you don't, that's completely okay. It just means that we have double bonds. Double bonds can be in the cis or trans configuration. What was the other terms that we can use instead of cis and trans? Easy, exactly. More specifically, we're always going to be using easy, okay? So let's just get used to that format.
What's the difference between using diastereotopic, like in terms of
ENC is more specific. It's whenever a double bond is at least tri-substituted, because for cis and trans, we only use those terms for a double one that has two groups, only two groups.
And ENC could be more than two.
Yeah. Okay, now, these guys, if we switch, whoops, let's say, the hydrogen on top, this one in here, orange, or chlorine, what do I form? E or C? The one on top.
She's about it, she's explaining it right
Groups in place of.
E because they're opposite to each other. E means strength.
I'll
So
see.
yeah,
He was
it's gonna be your major group on the left side, on the right side, the whole thing at the bottom. So opposite sides, E. And then if I repeat the same process with the hydrogen at the bottom, the one that's in red, I form the C isomer. So because I form both things at the same time, they're separate signals. More specifically, if your professor were to ask you for the relationships, which he's gonna ask you in the exam and quiz, they're diastereotopic to each other.
Sorry.
Yeah.
I'm a little rusty on the ENC. So these shows, you said that it was E trans, how true?
Yeah. Damn.
Okay.
You were saying, you
I don't know.
In a bit, but so the somebody has an PhD based on high priority group and so I forgot to determine a higher priority group, does that mean it's more, to like, more atoms?
Not one is right here.
So what's the higher?
Yeah.
This is.
Yeah.
So, in here, once we expand, we touch the carbons, they're the same exact way, right? So you're gonna keep expanding until you find a different overall weight number in the product. Yeah, so because the bottom one is more heavy than the other one. Okay, guys, news, we're all gonna pack up and we're gonna go downstairs to room 103. And I apologize for this, but we're confusing upstairs in here. It's a lazy happen.
What time is it? This one?
No, the answers are gonna be posted after we're done with the handout. But the recordings are available, so you can be, all that again, and how we explain it. But I did notice that, since again, we're a lot of people, so probably most of you are not fully aware of what we covered, which is completely okay. Now, the portion here on the top, what was mostly just words. That one, I do encourage you to look at the recording because it's very simple. It's basically just reading that. But what I'm gonna go over again is this bottom part, okay? The aspects of NMR. Because if we don't have a good foundation on that, we can't proceed with a handout, okay? So again, for each NMR, we have 4 different aspects. First one, the one that we were practicing, was the number of signals. Again, number of signals is just unique environments, unique connections that you have. And distance sometimes is gonna be involved in it. Now, next aspect, the easiest one, integration. What's integration specifically? You said it in class today. Area of 100? Area under the signal, yes. You might get a question on the definition of integration, so keep that in mind. Now, integration, again, it just gives you the number of hydrogens that you have per signal. So if we have a methyl group, for example, what's gonna be the integration for a methyl? It's gonna be 3H. That's it. Simple as that. You're just counting hydrogens. Now, next one is gonna be your chemical shift. He was talking about that one today and he went into more depth on this one. Now, chemical shift is just the ppm values, which means that you have something that's D-shielded versus shielded. Hopefully you guys know what's the difference between them, but what's D-shielded? What does it mean? What does that feel mean? What does that mean though? So yes. Now, D-shielded in a more simplified term is basically whenever you're close to anything that's very electronegative or electron dense. So basically, whenever you have something that's very electron dense, it's gonna be pulling away all of the electron density, leaving that hydrogen exposed. That's why they're D-shielded. Shielded, complete opposite. Those guys are very protected. Okay. So far, questions on those guys. chemical shift, integration, number of signals. This is basically a review from Orgo 1. Now, last aspect is multiplicity slash splitting. They mean the same exact things. It's either word, you know what to do. Now, multiplicity, it's all about your neighbors. The rule was n plus 1. N was just the number of neighbors that you have. Now, to find neighbors, those guys are going to be adjacent to the signal that you're looking at. Yes, but they have to be within 3 bonds. If you pass 3 bonds, that's not going to be considered a neighbor. If you touch a hydrogen within 2 bonds, that's within 3 bonds. So of course it's going to be a neighbor. Okay, so keep that in mind. Now, the rule that you see at the middle about heteroatoms. Heteroatoms for this class, they're going to be blocking agents basically. So you can't go past them to find any neighbors. But if you're taking labs, sometimes you're going to see that that can happen. But again, always ask your TA because in some spectrums, you're going to see that. Okay, so far, questions on the aspects. Do we remember them? Okay, some notes. Okay, now for CNMR, what are the aspects of CNMR? Are they the same exact? So I have integration, number of signals, chemical shift, multiplicity. Bueno. You are not going to see multiplicity with CNMR. What else? The chemical shift is going to be different numbers, but that aspect, it's going to be there. It's just going to be a different range of numbers. Is that no multiplicity or splitting? So what other aspect is not going to be on CNMR? There's no integration at all. So the only aspects that you're going to find in CNMR is just number of signals and chemical shift. As far as chemical shift goes, the ranges are going to be way different from each other, okay? So far, yes. If you look at the carbon spectrum, it's just going to look like plain straight line. That's the only difference physically on the spectrum. Now, why exactly it happens, I'm not quite sure. So you would have to ask your professor on that. Probably that too. But again, I'm not gonna say it for sure because personally not know it. So if you want to know that, it can be in your book. If it's not there, you can ask your professor. Okay. So far, questions on the aspects. We're good. We remember them. Okay, gonna move on. Now, we were talking about A, right? No, A, number of signals for HNMR, again, unique environment. We were okay with these two guys, the methyl group and the little hydrogen there at the bottom. Now, the hydrogens on the double bond. We were having some trouble trying to find the E and C isomers. Now, remember, all that I'm gonna do is something called the Q test. What was the Q test? Do you guys remember? What did it entitle? Just crickets? No one? Q test. We were talking about chlorine upstairs. Yeah, we're basically just gonna swap whatever hydrogen we're in doubt about, or anything. It can be a Q, yes, or it can be chlorine, for example, any atom that you want. So I'm gonna cross it out if I put a chlorine here. Now, if you don't remember this, that's okay, but we have to start to get comfortable with this, findings and trends configurations. So first thing that you're gonna do is split your double bond right in the middle. Now, we have two main sides on that double bond, left side and right side. On the left side in here, we have a connection to a chlorine and a hydrogen. What's heavier? Chlorine. So because that's heavier, that's gonna be priority number 1. Now we repeat the same exact process to the right. This carbon on the right side is connected to 1 carbon and 2 carbons. They're different. Yeah, between the carbons. No, they're the exact same. So what do? We keep expanding. Now, what's gonna be heavier? The chain at the top or at the bottom? Bottom. So that guy is gonna be my number 1. Now, as you can see, your priority number 1s, they're pointing to opposite sides. So that means that this is gonna be the trans, or more specifically, the E isomer. Okay, do we all see that? Okay, seems like it. Now, if you repeat the same exact process for the one at the bottom, chlorine And now that means that this one, it's back to hydrogen. Now your priority number one is at the bottom. So if they're both pointing to the same side, this is this slash C. Okay. Questions? We're good, we remember it? Yes. Because you have to see if you're creating both isomers. If you're only creating one of those isomers, then that's not gonna be diisotopic. They're not gonna be different signals for that reason. We're gonna see more examples of that later on, so hold on to that question for now. Okay, now this one. For B, again, first thing that I have to do before looking at the environments, it's symmetry. In that case, we only have one plane. So that means that again, I only look at one of those sides. Now, we start from the top. We have a method group, unique environment. Then we have the little baby hydrogen that a lot of students forget. So please do not forget about this one in here, the green one. That's in the junction of the carbons. Now, on the bottom of that one, why are we not gonna have a hydrogen there? Yes, right here. Because there's already 4 bonds. So do not always assume that just because you have a little junction in there, there's always gonna be a hydrogen. Keep in mind that carbon can only have 4 bonds in total. And now for the rest of the hydrogens in here, these guys are gonna be different from each other because they're at different distances from the method group. The orange one in here, that one is way closer to the method group as compared to the yellow one at the bottom. Okay? So again, it's all about connections and their distances. That's how you know that you have different signals. Okay, so far, questions on the recap of those 2 molecules? We're good? We're not good? You guys can speak up. You can ask as many questions as you want. Okay, looks like we're good. Now, same process for molecule C. Now, the main difference between this molecule and the rest of them was that stereochemistry was shown. So, because stereochemistry is shown, remember, wedges and dashes is all about a 3D plane. So wedges, those guys are coming towards you, right? Dashes, they're going away from you. So in this case, if we compare these 2 hydrogens in here, they're connected to the same carbon, yes, but one of them is on a wedge, this one in here, so it's way closer to the alcohol group that's also on a wedge on this side. Now, the one here at the bottom, the one that's on a dash, that one is a little further away because that one's pointing down as compared to the alcohol group that's pointing up. Okay? So again, whenever you see stereochemistry shown, please be careful with that. He's probably gonna try to trick you with stereochemistry at some point. So just keep that one in mind. But so far, questions on A through C? We're good? Okay. Now, for molecule D, do we have any planes of symmetry? Yes, how many? You have 2. You have one right on the middle and right across from it. Okay, now for H and MR, how many total signals do you see? You just see 2, the ones in the method group, and then the only other hydrogen that sits there, just 2 hydrogens. Now, what about CNMR? It's gonna be 3 CNMR signals. We have 1, 2, and 3. And again, I'm only looking at one portion of the whole molecule, again, because of symmetry. Okay. So far, questions? We're good? We see it? Okay. Now, molecule E. Do we have any planes of symmetry? I heard a no and a yes. Which one is it? Yes. It's right down here.
I have a question.
Planes of symmetry are not gonna be completely horizontal or completely.
I have a question. Excuse me.
Here, for H and MR,
Hello?
we see the ones in the method group,
Shannon?
that's right in between the 2 method groups. And then the ones that are starting to go down.
Shannon?
Questions on H and MR? Again, it's all about connections and distances. Now, what about C and MR? How many signals do you see? 5 or 3? I hear a 3. It's gonna be 5. Again, we're just counting the carbons. We have one here, second here, third one, fourth one, and last one, fifth one. Okay, so far, questions on that? Do we all see that? Are we starting to get more comfortable with counting signals? Yes? Okay. Now, F, how many HNMR signals do you see? For F. For HNMR. 3. What about CNMR? 4. Beautiful. Now, let's break it down. First of all, are there any planes of symmetry? How many? 1, right down the middle. So that means that, again, mother group, 1 single environment. Then hydrogen, and then the other little big hydrogen, okay? Pretty simple. Now, as far as CNMR, again, it's just counting the number of carbons that you have on one of those sides. Now, for G, do you have any planes of symmetry? No. Okay. How many HNMR signals do you see? It is gonna be 3. What about CNMR? 3 as well. Okay, so let's look at this molecule again. For HNMR, first one, that little hydrogen sticking out of the carbonyl group. But first of all, what kind of functional group is that? Functional group, what's the name? It's an aldehyde. You guys have to remember those terms. Aldehyde, ketones, all of those guys. Okay. Now, next one is the little baby hydrogen here in the middle, the junction. And then we have the mother group. But what about the little hydrogens in here on the top of the mother group? Why are they not different? Exactly. There's a little plane of symmetry right in the middle. Now, keep in mind, single bonds, they constantly rotate, meaning that they're going to be exposed to the same exact environment. Okay. Again, keep that in mind. If that was a double bond, then they would be different because they're locked in a certain configuration. No. 1, 2, and 3. Again, we're just counting the carbons for CNMR. And in this case, same process. The one on the bottom and on the top of the method group, those guys, they're the same exact thing. Again, because of that rotation that we have. So far, questions on that? Question in the back. There's only 3 HNMRs because the hydrogens here on top, they're going to be the same exact as the ones in the method group at the bottom. Okay. Okay. So far, questions on that? We're good. We have 2 more minutes, so I'm gonna stop right here because those ones are gonna take a little bit more time. But if you didn't try them on your own, please give them a try, and we're gonna work on them on Friday. And again, I apologize for all of them moving around. Okay, so for Friday, I will be sending an announcement, okay, about the location of it. We're probably not gonna be up there because it's just too many people.